And it's 4 o'clock now, so we can start. So what we're doing today is we're answering questions, and we're doing the review slides. And I also heard through the grapevine what your assignment is, and I thought, oh, I covered that. And I figured this is a review class, let's review what we covered. All right? So calculators, right, happened just as I started high school. And the first calculators were in reverse Polish notation. I don't know how Polish comes into it, but right, so the way, if you want to add 1 and 4 together, right, the way you do it now is 1 plus 4. But the way you did it there is you push 1 on the stack, then you push 4 on the stack, and when you hit plus, it pops the top 2 guys off and adds them and pushes the result, right? So here you do that, and then when you do, you do 2, and then you do times, right? People kind of buy that? And from the tree, you can think it's you're printing the tree in postfix order, right? What's postfix order is you print the left, then you print the right, and then post, you print the root, right? So you print this. How do you print this? Well, you print this, and then the root, right? And then you print the other child, right? And then you print the root, right? People buy that? Everybody? So, oops. So how are we going to implement it? Right, so here is right, there's that tree, and I don't know. So, oh yeah, this is the traversal, right? You first print the left tree, and then you print the right tree, right? And then you print the root. That's post-fixed order. And now we're given this string. I mean, this is the kind of string you're given in the test, right? In the assignment. I guess you're given it as a linked list just to make your life a little harder. And now what I'm asking is to give the result, right? And what you're supposed to do is build the tree, right? So let's do it, right? Oops. All right, so I'm big on loop invariance or system invariance, right? So what the invariant is, the guys that you haven't, I don't know quite how to word it, but the guys that you haven't dealt with are on the stack, right? I have to think best how to describe it, but you get a 3 and you push it on the stack, and then right, then all that stuff happens, and the 10 goes on the stack, right? Right. So this is, if I were going to do your what you've done so far, right? I would say the 3 is on the stack, and not only the 3 is on the stack, but maybe 3 is some big tree, right? Remember, the whole tree, right, is going to be some big thing like this. And what you think is, well, we're going to handle the left subtree. And when we handle the left subtree, we're going to build the tree structure for it, right? And what's on the stack? Let's go back. right? So this is we go down to the left tree, and it's some big, ugly tree, right? And so you handle it. And then when you're finished with the tree, what's on the stack is, well, I'm saying the evaluation of that tree is on the stack, but you need to create a tree, right? So what you could have here is a pointer to the tree that you created, right? You read in this whole tree because it's the first part of the list. And when you're done reading this whole tree in, the loop invariant is that here there's a pointer to the tree that you created, right? Does that make sense? And then you read in the next. And how did you read in the next? Well, you read the 1, and the 1 goes on the stack. Then you read the 4, and the 4 goes on the stack. And then you read the plus, and the 1 and the 4 come off. And what do you put on? You put on a pointer to the tree, which is the plus 1 plus 4, right? That's what's here is the tree. And then you read the 2, and the 2 goes on, right? And then you read the times, and the 1 plus 4 comes off, the 2 comes off, and what goes on back on is the tree. You know, I'm putting in the value 10, right? But what are you putting in here? You're putting a pointer to this tree structure, right? Does that make sense? And then what do you read next, right? You read this times. And what do you do when you read the times? Is you pop the top 2 things. And what are they? They're both pointers to trees, right? Here, where does the times go, right? The times go there. So when you see a times, the loop invariant is that the thing on the top of the stack is a pointer to the right tree. And what's next on the stack is the pointer to the left tree, right? So you pop these 2 pointers off, and what do? You create a tree whose root is times, and whose left subtree is the second thing you popped, and the right subtree is the right thing you popped, right? Is that making sense? Right? So you pop them off, you create this bigger tree, and what do you push back on? You push back on a pointer to this tree, right? So the code won't have to be very long. Yeah, so if I were going to do a fancier parsing thing, like if I was going to have brackets and I'm going to do it in, right, normal ordering, I would need to do it with recursion and with a fancier algorithm than we're covering here. But this guy works as I call this an iterative algorithm, right? What's my loop invariant? I figured out my loop invariant now, is that when I get the times, what's the loop invariant when I get the times? Is that the left subtree of times is this guy, and the we got the right subtree and then the left subtree, right? That's my loop invariant. So it's an iterative algorithm with the loop invariant, right? And you know, I'm really big on loop invariants. The loop invariant's true. What does that tell me? That tells me I just read a times, and this is a pointer to my right subtree, and this is a pointer to my left subtree. I don't know what's here. It's none of my business, right? This is what my loop invariant tells me. And what do I have to do? I have to make some progress right? Not exit, if we haven't exited. And then I have to get the loop invariant again, right? So how do I do that? I pop this guy, I pop this guy, I build a tree with left side, right side, and then I push this onto the stack, right? And then you kind of argue, well, this maintains the loop invariant, right? And of course, loop invariant has to talk about what's all this other stuff, right? But not in a way we want to think too hard about, right? Does that make sense? Yeah, yeah, right. I mean, if you want to do it to yeah, I mean, the truth is, stacks. What is recursion? Recursion uses a stack, and we're using a stack, right? So, if you want to do this recursively, right, you're going to have to call your left friend, right? I mean, so suppose this was our input. I have to call my left friend to read the 3 and build a tree, right? And then I have to call another friend to read this bit, the second circle bit, and to build a tree. And then I read the times and put them together, right? Now, the hard part is knowing where these splits are. All right. So actually now it's not so hard. Let me tell you how I would do it recursively. Right. So I have some really big long string. This is my input. Right. And I'm not going to do it forwards. I'm going to do it backwards. I'm going to see what's the last character has to be a times. Right? No, it has to be an operator. It has to be an operator, right? So then there's going to be, it has to be of the form some split. I don't know, maybe I don't know how to do it. There's some split where it's this times this, right? So you have to figure out where that split is. And that might be hard, unless you're doing something fancier. To do it fancier, we'd have to bring in context-free grammars, and we'd have to, I don't think it's worth it. Yeah. Yeah, even if it's not a linked list, right? You got to somehow find the split, right? And then you get your left friend to build this and your right friend to build this, and then you build your tree. And just off the top of my head, I don't know how I would find that split. Everybody good with this? Everybody think you can do it? Are there any other, is it just one question? I only got one question. Yeah? Yes. Yeah. This was just getting ready for Monday.